All right. So this next section that we're getting into, it's a section titled Related Rates. With this section, there is no real new theory that we're introducing. So there's no derivation for me to perform for you. Instead, it's going to kind of give you a taste of what it's like to solve physics problems. What's going to happen in these problems is we're going to be given some story problem. The hard part is going to be coming up with your mathematical equations to represent this problem. The problems are going to relate two variables to each other. You're going to take the derivatives of both sides of your equation, which is going to give you a rate of change of both those variables, and it's going to tell you how they're related to each other, hence why the chapter is called Related Rates. So that's the way you're going to solve these problems. So there's nothing for me to The hard part about this is there is no, just follow this procedure and you'll solve the problem. There's nothing like that. You have to just look at the problem, think about the problem, understand what the problem's telling you to do, and figure it out. So give you a bunch of examples of me just walking you through that exact process. So here's our first problem. And we're just going to write down information as we go. So water runs into a conical tank at the rate of 9 feet cubed per minute. Now 9 feet cubed per minute, what is that? That is the rate at which the volume of the water is changing in my cone-shaped container, my cone-shaped tank. So far, I was told that our tank is cone-shaped. So it's going to be something like this. Pictures lie, don't read too much into the picture. I know that I have water running into this tank. So here's my water level, however high the water is. And my water running into the tank is coming in at 9 cubic feet per minute. So the change of volume of my water with respect to time is 9 feet cubed per minute. So scribbling that down to the side here, so given information is that the change in my volume with respect to time is equal to 9 feet cubed per minute. Okay? Yeah. The tank stands point down. Okay, we kind of assumed that, but good that they told us because our tank could have been two ways. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. So this tank right here, I know that this tank, however tall it is, I know it's 10 feet tall, and I know that the radius of my tank at the top is 5 feet, right? Yep. Sorry, writing kind of small. Should have drawn my picture bigger. 5 feet. So 10 feet tall, 5 feet is the radius at the top of it. Let's see, what else does it give me?
That's all it is.
How fast is the water level rising when the water is 6 feet deep? So it's telling me how deep this water is right here. What variable should I use to represent how deep my water is?
Doesn't it tell you 6?
It doesn't matter what variable I use. I'll say how high up the water is. I'll use a y right there.
Okay.
The height of this water is changing over time because we're constantly filling it up. The question is, how fast is the water level going up now? So now I'm looking at the change in my height with respect to time. I'm looking for what this is when I know that my height is what?
66.
6 feet. And I think we have all our information written out here now, right?
Yes.
So we can ignore that for a second now and just focus. So here's one rate of change. Here's another rate of change. I somehow need to relate my volume to my y. That's what this problem is screaming for me to do. Somehow relate the volume of my container to my y. Now we're looking for, intuitively, how fast is the water level rising when it's 6 feet deep. Notice that the water level, it doesn't rise at a consistent rate. If you were filling up this cone, when the cone's really small right here, a little bit of water goes up really fast. As you get closer to the top, a little bit of water fills it up just a little bit more. So in 1 minute, it might go from being 0 feet deep to 5 feet deep. The next minute, it might only go from 5 feet deep to like 7 feet deep. So the rate at which the water is going up is constantly changing. We want to find how fast it's going up when the water level is exactly 6 feet deep. Okay, so obviously, I'm using the volume of a cone. So that's a good equation to start by writing out. What is the volume of a cone equal to? What is the volume of this water right here? Let's say that this water has a radius of small r. So what is the volume of my water?
Is it 4 pi squared or 4 pi r squared?
That's the surface area of a sphere.
Oh, I don't.
We're talking about volume, so it has to be cubed somehow.
Oh, yeah.
What's the volume of a cylinder? If I have just a cylinder here
It's going to be,
with height y, and we'll say it has radius r right here.
it'll be the area of your circle times your height.
It's just the area of the circle times the height, area of the base times the height.
Okay.
So in that case, our volume would just be area of the base, which is pi r squared. That's the area of the circle, times the height, y.
So it's going
Now
to
notice that r is going to be in terms of meters or feet or something like that. Y is going to be in terms of meter or feet or something like that. And so you're going to get units cubed. Volume better come out cubed units or you done messed up.
yeah.
Okay.
Uh,
Now for the volume of a cone, it's just 1/3 that.
okay.
So the volume of a cone is just 1/3 the volume of the cylinder.
Right.
That's something that we can derive when we get to integrals in chapter 6 fairly easily. But we won't bother deriving it now. Okay, so the volume then of this cylinder right here, nothing different. I'm going to write it instead of 1/3 pi, I'm just going to write it as pi thirds
Okay.
times r squared times y. Now, notice that we know the ratio of the height to the radius of this cone. We've got to use that information somehow, some way. How does the height relate to the radius?
Twice. It's half.
The height is double the radius, or the radius is half the height.
Right.
So how does y relate to r?
It's going to be,
Gonna be twice as big.
Y is equal to 2r.
Okay.
You with me?
Good.
Or in other words, r is equal to y halves. Whichever way we want to write it, doesn't matter.
okay.
Here's my volume. I've got to relate v to y. These are the two rates of change I'm trying to relate to each other.
Right.
So I've got to, volume is some function in terms of y. So I've got to get rid of that r and somehow express it in terms of y. Here's how I'm going to do that.
Oh, okay.
Oh, gotcha.
You with me?
Yeah.
So I'm going to get that my volume is equal to pi thirds. R squared now is going to be y squared over 4.
Y over 4. Oh, okay. Never mind.
You got to square the 2 times y. You with me?
Yes.
Which is going to be equal to pi 12ths times y cubed. Good?
Yeah.
The y to the y gives me the y cubed. The 3 times the 4 gives me the 12.
Yeah.
Okay.
Good?
Yes.
Now I'm just going to take the derivative with respect to time of both sides. What is the derivative of v with respect to time? It's dv dt. That's the derivative of v with respect to time. Now let's do the derivative with respect to time of this thing. Right, here's just a constant, we can ignore that. So what's the derivative of y cubed with respect to time?
3y squared.
So we'll write pi 12ths times 3y squared times, come on, what did we do last week?
The chain rule.
Chain rule times the derivative of y with respect to t, whatever that is. Always and forever the chain rule.
Yeah.
Okay, so now simplify the algebra a little bit here, and I get dv dt is equal to pi fourths times y squared times dy dt. Now what are we looking for? We are looking for dy dt when y is equal to 6 and dv dt is 9. So plugging all that in, ignoring units, not going to bother writing out my units, we get 9 is equal to pi fourths times
Y squared, 6 squared.
36.
36 times dy dt, what we're solving for.
Yeah.
Yeah.
Okay, so I'm going to multiply this side by 4
Okay.
Okay.
and divide it by 36.
Okay.
Okay.
What does that give me?
1.
1, and then divide it by the pi. So I get 1 over pi is equal to dy dt. You see it? Yes, we're missing Audrey.
That's it.
And it's 1 over pi, should have written this different, dy dt is going to be equal to 1 over pi
Meters cubed.
meters per minute. That is how fast the water level is going up here.
It's feet. It's feet per minute.
Oh, is it feet? Thank you.
It's feet per minute cube, isn't it? Or feet cube per minute?
Yeah.
No, because it's one.
Is that the height? Or, that's the height. Oh, that's the height.
Over here, if you wanted to follow the units, maybe it's worth it once to write out the units, but when it's all said and done, it's always going to come out how you expect. What were our units here on the 9? Rewriting that was 9 feet cubed over minutes is equal to, over here, we had pi over 4, that was just a constant. The 36 here was 36 feet squared. And now, and then we had dy dt. So divide by feet squared, and you're left with feet per minute on this side. So dy dt, this was times the dy dt, right?
Yeah.
Right.
Dy dt. So when you divide over, the feet squared come down here,
I got you.
and so you get 1 foot, 1 minute, feet per minute. And the units will always come out exactly the way you expect.
So, okay.
Any questions on that? So obviously the hard part was probably setting this up. Once you did that, everything else is pretty easy. So the hard part is going to be coming up with the mathematical way to represent the problem. Solving the math after that with these problems is usually pretty straightforward.
Yeah.
Physicists often joke that once they're going along on a problem, they get to a point and they say, and the rest is just math. We've done the hard part. Now we can just calculate it and we don't have to keep on thinking about how to represent and model our problem. So that's what's going to make these hard, is coming up with the way to model the problem. So let's do another one. I guess we probably should have written out what that approximates. So he got 1 over pi, approximately 0.32.
Yeah. I see.
Okay. Next one, don't want to look at anything the author gives us because we don't want him to taint how we would internalize a problem. Okay, so a hot air balloon is rising straight up from a level field. Sorry, a hot air balloon rising straight up from a level field is tracked by a rangefinder 150 meters from the lift-off point. Okay, so what have we got here? Try and draw my picture a little bit bigger. We've got some hot air balloon. So here's the basket to it. Always helps to start out by drawing a picture for it. And this is coming up from some liftoff point. That liftoff point, here's our ground, is 150 meters away from some rangefinder.
Okay.
So I know this is 150, was it meters?
Yeah.
Meters. Okay, and our rangefinder is obviously pointing at our hot air balloon. So that's going to create some angle theta that we're going to end up caring about. Let's keep reading. At the moment, the rangefinder's elevation angle is pi force. So the time we care about is when theta is equal to pi force.
Yep.
Oh.
The angle is increasing at a rate of 0.14 radians per minute. What is 0.14? What is that number?
Hi.
It's.
Oh no, that's true.
What is that telling us? It's telling us how much the angle is going up. It's telling us a change in the angle.
Oh, the rate.
How do I write the change in the angle?
0.4 radians.
Well, that's the number, but what's the symbol? So it's not giving me theta, it's giving me the change in theta with respect to time. That is giving me d theta dt.
Right. Okay.
So d theta dt at this theta is 0.14. Right? How fast is the balloon rising? Okay, so we need to talk about how fast it's rising. If we're going to talk about how fast it's rising, that's going to be the change in height with respect to time. So we need to model the height. What variable should we use for the height here? H. I'm just going to use y again, but h is fine too. Okay, so that's all our information from our problem. I somehow need to relate theta to y. That's my whole goal here. So looking at this picture, how can I relate theta to y?
Sine.
Well, sine uses hypotenuse. I don't have hypotenuse. What do I have? I have the base and I have the height.
Tangent.
So, okay.
Tangent. So I know that tangent of theta is equal to what?
Y
y over
Whenever the number is
150. Perfect.
Yeah.
Ignore units for a second. Or in other words, this gives me that I want to write y as some function of theta. So I'm going to say y is equal to, oops, forgot my constant, 150, tangent of theta. Good?
Okay, good.
Okay, now I need to relate the change in y to the change in theta. How am I going to do that?
Find them.
Derivative.
Take the derivative of both sides.
Yes.
Yeah. So what is the derivative of y with respect to t?
It's dy over.
It's the derivative of y with respect to t. Okay. Now let's take the derivative of this with respect to t. 150 is still just 150, that's a constant. What's the derivative of tangent of theta?
Negative. There's like sine, negative.
Negative. Secant.
It's positive. Secant
Secant.
squared of theta
Okay.
times
Uh,
chain rule.
d theta over d.
Oh.
d theta dt.
right. This is function. That's right.
Always and forever. Remember, going all the way back, even if I had tangent of x, and I was doing its derivative with respect to x, what would the answer be? It's secant squared of x times the derivative of x with respect to x. In that special case, dx dx is 1. And so we ignore
That's
it.
right. That's right.
That's a very special case. We always do the chain rule. It's just a lot of times the chain rule comes out 1.
Okay.
That's one way to think about it.
Right.
Okay. So, always and forever, apply your chain rule. Can never hurt, will only help. Alright, so now we've got this equation. And now what were we looking for? We're looking for dy dt when, oh, did we have the y? No, we don't, it doesn't depend on y. We don't care about y.
Yeah.
So dy dt, it depends on theta and d theta dt. They gave us a theta, they gave us a d theta dt. We can find the dy dt at that time.
So we just plug it in.
So we just plug it in. And I don't know if there's much use in writing much more out. Let me get my calculator. And I'll start by just plugging stuff into my calculator, telling you what I'm plugging in. So plugging that into our calculator, I'm going to type out 150 times, I don't have a secant button, so I've got to write that as 1 divided by cosine. Cosine of what angle?
Theta.
Pi fourths, because we're actually plugging into our calculator now. Pi fourths, so 1 over cosine theta of pi fourths. I got to square the whole thing, and then multiply it by what? 0.14. So 0.14, and when it all comes out, the number that it's spitting out for me is equal to 42.
Exactly.
Yep.
Answer to the
Think about secant at pi fourths is going to be exactly root 2 over 2. Square that by itself is going to be, that one comes out exactly 1/4. Okay. Anyways, so not too surprising it came out exact. This was meters per whatever our unit of time was that we were taking our derivative with respect to. So second, assuming that this was seconds. I don't remember what it said there. Did it say seconds?
I think so.
It said radians per minute.
Oh.
Radians per minute, so this is going to be minute. The time unit is whatever the time unit was over here.
Yeah.
That's ultimately where our time unit comes from.
Yeah.
Okay,
Question.
go ahead.
When we take the derivative of both sides, why does the 150 go to 1?
Because it's multiplied.
Because the derivative with respect to x of some constant times f of x is equal to c times f prime of x. That's one of the things we proved. You can pull a constant outside of your derivative when it's product.
Oh. Oh, okay. Okay.
Remember that the derivative with respect to x of one thing times another thing is not equal to the derivative of the first times the derivative of the second.
Yes.
You could apply your product rule here. One of your terms goes to 0, and that's going to be your other term. Namely, your first times your derivative of your second, plus your second times the derivative of the first. So, however you want to think about it.
Okay.
Any other questions? Okay, let's do another example. So, example 3. All right, this one's got a lot going on. We have a police cruiser approaching a right-angled intersection from the north. All right, so I've got my right-angled intersection.
North is up.
I'm going to make north up. I don't know
East is
if we're going to be going right or left. Is the other direction east or you see it? East?
You're good. You got it.
Okay, so we've got one car coming this way, our police cruiser. Police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner and is now heading east. When the cruiser, so the cruiser is our police cruiser, so what's its distance here?
0.9 miles.
0.9 or 0.6?
0.6 miles north.
So that's 0.6 miles. Then our other car, which is heading to the right, is 0.8. So that one's a bit more this way. Here it is. It's going that way. And this distance here, we know is 0.8. Okay. Let's see. The police determine with radar that the distance between them and the car is increasing at 20 miles per hour. If the cruiser is moving 60 miles per hour at the instant of measurement, what is the speed of the car? Okay, so we got a few things going on here. I've got to choose what I'm going to call the distance between my car and this.
Which is your hypotenuse?
So I'm going to call this distance here y. We care about the time when y is equal to 0.6, right?
Yeah.
I'm going to call this distance here x, and we care at the time that x is equal to 0.8.
Okay.
With me?
Yeah.
Yeah.
We know that dy dt at the time we care about is equal to what?
dy dt is
How fast is the police car moving?
60 miles per hour.
Is it 60? Here's a big gotcha.
it's 40
It's 60.
squared.
No.
6 miles per hour.
Is our y increasing at 60 miles per hour?
Decreasing.
It's decreasing at 60 miles per hour. So our change in y is minus 60.
Wow.
Why is it decreasing?
Because the car is getting closer and closer to the intersection. Y is our distance from the intersection to our car. So dy dt is negative 60.
Okay,
That would have been an easy one to get stuck on and keep getting the wrong answer forever. Okay? And now finally, we need to relate the distance from our police car to here.
Yeah.
Now, that distance, I'm just going to represent with the variable s.
Okay.
Right? And we know that at the time we care about, ds dt is equal to what?
20.
20. The distance,
Wait. What is it? The distance between us?
We're looking for the speed of the
the
car.
police determines with radar that the distance between them, the distance between the police car and the car it's chasing,
Oh, I see.
is increasing at 20 miles per hour.
Okay.
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 So, sanity check right out the door. This car better be going faster than this car.
Yeah, right.
Maybe. I don't know. Maybe that's still not true because of the angle between them. So maybe. But we are looking for dx dt at this time. That's what we care about. Right?
X.
Right.
What's X referring to?
How far this car's moving. This car is x away from the intersection. So dx dt is our change in x, our change in how far away that car is with respect to time.
Which is the speed of the car?
Which is going to be the speed of the car. That's how it's changing its distance. If the car stopped, x is no longer changing with respect to time. X is our distance from the intersection to the car. Alright? So already we've done a lot of what's considered hard stuff. Internalizing this picture right, identifying our variables correctly, deciding how we're going to represent this. Now we're missing one crucial equation, obviously, which is how do I relate my s to my x and my y? So s is equal to, what is s?
Is the hypotenuse
Are we doing
right
the-
triangle?
Right, so what is it?
X squared plus y squared.
That's
Or it's the square
Under
root.
the radical.
It's the square root
Yeah.
of x squared plus y squared.
Right?
Yeah.
So now, because look, ultimately what I need to do is I need to relate these three rates of change to each other.
Yeah.
Which means I need to relate s to x and y. Here's the equation that relates s to x and y.
Duh. Yeah.
Oh, duh. Now, what are we going to do?
Solve it.
Plug in.
Neither.
Take the derivative.
We're going to take the derivative of both sides. Here's how s is related to x and y. I need to figure out how ds dt is related to dx dt and dy dt. So I can solve for my dx dt.
Okay.
Okay, so taking the derivative, what's the derivative of s with respect to time? It's the derivative of s with respect to time. Okay, how do we do this? Maybe help you to think about this one for a second.
Isn't it
This is the same thing as
parentheses
x squared plus y squared is 1/2.
Yeah.
That helps you think. So what's the derivative? Come on.
You subtract 1, so that's negative 1/2.
First, bring down the 1/2, right?
And then, yeah, 1/2
Multiply by
x squared
whatever you had
plus y squared. And then that's negative 1/2.
minus 1/2
And then you times it by
And
the
then we
derivative.
multiply
times
by
the derivative of the inside.
2x plus 2y.
So close. 2x
Plus 2y. What?
2x times x.
dx dt. Chain rule, always and forever. Plus 2y
Oh.
dy dt.
Or dy dt.
Finish your chain rule. Always and forever.
Power. We're going to
If you're going to take derivatives, you better end up with derivatives.
Right.
Yeah.
Okay, now let's clean this up a little bit in how we write it. Notice that I can factor the 2's out of here, and they'll cancel out with the 1/2.
Oh, that's right. Yeah.
So we can ignore the 2's and the 1/2. That will cancel out with that and that. Okay. X squared plus y squared to the negative 1/2 is the same thing as positive 1/2 we put in the denominator, which is the same thing as just over square root of x squared plus y squared.
Over 1?
So here's this term. So that's a negative 1/2, right?
Yeah. So
If I put it in the denominator, that makes it a positive 1/2, which is the same thing as the square root.
What's on the
yeah, that.
I haven't done my numerator yet, just wrote that term. I still need to do these terms.
Okay.
Okay, in my numerator I have x times dx dt plus y times dy dt. Good?
Okay.
Okay.
And ds over dt is on that too, right?
Sorry, what?
ds over dt is there too.
Oh, sure. I was just saying follow it down, but
Yeah.
that's fine. Okay, so now we're looking for dx dt. Right?
At the other two.
So I just need to, at all these points.
Yeah.
Yeah.
So I just need to
Plug it.
get this by itself and then plug everything in.
We have it. It's ds dt.
You don't. No, you're.
Well, just solve for this first. Get it by itself. So multiply both sides by this thing. So I'm going to have that ds dt
Oh, okay.
times the square root of x squared plus y squared.
Equals.
Well, you don't want to do it all in one go. Okay. X times dx dt plus y times dy dt. Good? Okay, subtract this to the other side and then divide through by x.
Okay, that makes sense.
Okay, so we're going to get that ds dt times, I don't know if you can already see this. I'm tired of writing this. What is 0.8 squared?
0.64.
0.64. What's 0.6 squared?
0.36.
And what's 36 plus 64?
1.
100, but then, yeah, 1 when we shift it. So that's just going to be 1. Square root of 1 is just 1. So this is just a 1. And I'm just noticing that and I don't want to deal with it anymore.
Okay.
Okay? So we got 1. So there's our 1. So we get a minus of
dy dt.
y times dy dt equal to
X.
dx dt times x, but I'll just divide by x over here. Good? And now, just plug it in and see what we get. What's ds dt?
20.
So I've got 20
Minus.
let me put, I need to start with the parenthesis because I'm going to divide the whole thing when I'm done. So parenthesis 20 minus
46 times.
0.6 times
negative 60
-60
over
divided by 0.8, and it comes out 70. So it was going faster. So our initial intuition was right.
Can you go over how you got 1 from that
So
square?
this is equal to 70. Sure.
That root again.
6 squared is equal to 36. 8 squared is equal to 64.
Okay.
Add them together.
You get
6 squared plus 8 squared is equal to 100.
Okay.
So 0.6 squared plus 0.8 squared is equal to 1.
Oh. I see. Okay.
That's all I was noticing.
Yeah.
So he gave us nice round numbers. Authors are usually kind of that way. Okay, so we got 70 miles per hour. Let's check with the answer really quick. My laptop went to sleep. He got, what on earth? That's a different problem. My book
Particle
jumped.
B moves.
You're right there.
Example 3.
Example 3, 70. Okay, so, and you see he's using our exact same thinking. We went through the same process we did. Okay, so 70. All right, so we'll do one more of these. We'll do just the last one. Usually it's the hardest one. And then
5.
move on our merry way. Okay, oops, let's not look at his solution, sorry. So example 6, we'll make this last one and then move on to our next section.
Okay.
Okay, figure, I guess we have to reference the figure because he's talking about the figure, so scroll enough that we can see the figure, but no more. Figure that shows a rope running through a pulley at a point P and bearing some weight W at one end. So kind of reset our picture here. So we've got some pulley hanging from a ceiling. Our rope comes off that way, whatever, and then it comes down. And then at the end of the rope, we've got some weight W being pulled down there. A rope, So here's our point P. Not sure we really care about that. The other end of the rope is held above the ground in the hand M of a worker. So we've got some guy standing here. He's holding the rope, and it's 5 feet off the ground. So this is 5 feet. I assume it's going to give us this distance.
X. It says it's 20
Suppose the pulley is 25 feet above the ground. Okay, so this right here is 25. That is 25 feet. Suppose the pulley is 25 feet above the ground. The rope is 45 feet long. So let me write that to the side for a second. Rope equals 45 feet. So we have it somewhere. Not sure how I'm going to plug that into my picture yet. And the worker is walking rapidly away from the vertical line PW at the rate of 4 feet per second. Okay, so our worker is walking this way. So I'm going to use X to signify how far my worker is in that direction. And so that is giving me that dx dt is what?
Actually 4 seconds.
4 feet per second, right?
Yeah.
So this is 4 feet per second. How fast is the weight being raised when the worker's hand is 21 feet away? So we're looking for it when x is equal to 21.
Okay.
Right?
Yep.
I think we got all our information from this problem. So I am looking for how fast the weight is going up.
Okay.
Right.
So I'm going to call this length of the rope, I need to call it something. I'm going to call that y.
Okay.
And so we are looking for dy dt. dy dt will tell us how fast up that thing is going.
Okay.
Okay, so this is what we're looking for. Question mark. We know that our rope is 45 feet.
Oh.
So let me use R to represent this portion of the rope.
And why?
Why do we, what's important about that? Why do we need to know the length of the rope?
Because y plus r equals 45.
Why do we need to know the length of the rope?
Yeah.
Because the longer our rope is, the more shallow the angle is that he's pulling at. The less rise there's going to be per unit that he's pulling that way. Or maybe it will be more the further he goes.
The angle would get smaller.
Yeah, the angle gets smaller, so now all his pull is going to be shifting in the x direction. None of it's getting eaten up by the y. So that's very much going to depend on the length of his rope.
Okay.
That's strange.
So y plus r is 45.
So we know that y plus r is equal to 45. Let's think. I'm looking for how fast this is going up.
You have how fast he moves and the length of the rope and the buffer.
My r here, let's think about r. My equation for r. R is going to be equal to, because this, we can think about making a right triangle here, right?
Yes.
The height of this right triangle is always what?
Y. That's y.
5.
No, y is this portion of the rope.
It's 20.
We're looking at this right triangle right here.
Oh, I got
As
it.
this
I
guy
was just-
walks,
Yeah.
It's 20.
this doesn't change, it's 20.
Yeah.
So r is equal to x squared plus 20 squared. You see that?
And you have your x. Oh, no, we don't. Oh, it's 21.
We know that we're talking about the time when it's 21. So I need to somehow relate y to x. That's my goal here. Right? So I know that y plus, better yet, I know y is equal to 45 minus r. You good with that?
Yeah.
Minus r. I'm just going to write that as 400.
Okay.
Because r is
Good? Now, dy dt. Question, is our dy dt going to be a positive number or a negative number?
dy dt is the change in height.
Positive.
It's the change in y. Is this length of rope getting bigger or smaller?
Smaller.
Smaller. So we expect our dy dt to come out as a negative number.
Positive.
Negative.
Negative.
If it's getting smaller, it's.
If the distance between, if it's getting smaller, then it's decreasing over time.
Okay.
That's a negative rate of change. So we expect this number to come out negative. Okay, so let's take our derivative. Just write this one more way to help you guys think. Right?
Okay, yeah, that helps.
Okay, so now we're looking for dy dt.
G equals 45.
45 does nothing,
That's right.
right?
It's not even timing it. Doesn't it just turn 1?
Yeah, it's not timesing it, so the derivative of 45 is
0. Yeah.
perfect. So derivative of this term, what do we do?
Is 1/2.
Minus 1/2, we still have the negative sign there.
Oh, that's right. And then
Minus 1/2 times x squared plus 400
The negative 1/2.
to the minus 1/2 times what?
The your derivative of x.
times
2x
plus
times the x over.
0.
dx dt.
Yeah. Okay.
Okay, there we go. This relates dy dt to dx dt. And which one were we solving for? We were solving for dy dt.
Right.
Yeah.
So we can now just plug in. And it's just going to spit out the answer for us.
Okay.
Right? Let me just write it one more way.
Does that 1/2 cancel out with the 2x over there?
Yep, so that and that go out. So just to write it one more way, this is x times dx dt all over the square root of x squared plus 400. Good?
Yeah.
Okay. So now we can write that negative. Don't lose my negative sign. Which we expected. We expected this to come out
Is
negative.
that a plus minus square root of x squared plus 400?
No,
Just positive?
just positive. It was always just a positive square root.
Yeah.
Oh, okay.
Okay. So we have, in our numerator, we have negative times x, 21, times dx dt is 4, divided by the square root of 21 squared plus 20 squared, or 400. Missing a parenthesis. Yep, there it is. And we get, comes out to approximately negative 2.9, I guess, if we're doing 2, feet per second. So, in other words, this weight is going up at 2.9 feet per second.
So,
Let me double check that with the author's answer. 2.9 feet per second. Okay, that's what he got.
2.9 or negative 2.9?
It's going up at 2.9 feet per second. This negative sign here is telling us that the rate of change of the rope
is negative.
of y is negative.
Right.
Because the rope is actually getting smaller that we're measuring. Your signs in these problems are often going to depend upon how you choose to represent this problem.
But it could be either.
But yeah, so there could have been another way to represent this problem where this came out positive.
Which is what I thought.
I could have instead used y to signify how high in the air this is, rather than this portion here.
Yeah.
And we could have solved the problem that way. And in that case, my dy dt now would be positive, because it's going up. Make sense?
Yeah.
Okay, so that is it for this section. Now stop the recording and get set up for the next section.
Yeah.
Yeah, okay, so 3.9 now is on linearizations and differentials. Fancy words, but you already should have pretty good intuition for what these things are.
Yeah.
So first off, what is a linearization of a function? Well, first off, what does linear scream at you?
It's a line.
It's a line. It's a lineization of a function. You're trying to force a line to represent some function at a point. That's all you're doing. Or in other words, it's just finding the tangent line of a function at a point.
Linearization.
Linearization. That's all it's doing. So when I say find the linear, here's some function f of x, right?
Yeah.
When I say find the linearization of this function at some point a,
Just find the tangent.
that means find the tangent line to that function at the point a. So you've already been doing this. Now, why do we do this? Why do we care? Why does it have its own fancy name? The point is, notice how well purple follows green really close to that point.
It's hitting the point.
Right, it hits that point, but a little bit to the right of the point, purple and green are basically the same line. And a little bit to the left of that point, purple and green are pretty much the same line.
Yeah.
So a lot of the times we have some functions that are kind of ugly to work with. We know the point, there's some point on the function that we care about, and we only care about values close to that point. We don't really care what the function is doing over here. We don't really care what it's doing over there. We want to work with the function, but we only care about it with values close to a single point.
Yeah.
This comes up in physics all the time. If you've talked about pendulums yet, you only care about pendulums when the angle's small. And so rather than dealing with the actual equation that represents the pendulum swinging,
Yeah.
you linearize it. And you say, this is close enough for the values that we care about.
Oh.
And so it makes your life easier. Later down the road, when you do calculus 2, we'll do something that's not linearization. Here's not what it's called, but gives you intuition. It's polynomialization, where we take some function that we hate, and we instead represent it with some polynomial function. Because we love polynomials, because they're so easy to take derivatives of, and on top of that, they're so easy to take integrals of.
Yeah.
We're going to find out integrating functions is not easy. It's much, much, much harder than finding a derivative.
Yeah.
But when it's a polynomial, oh, it's nice and easy. Derivatives, integrals are nice and easy. We love representing things with polynomials. So this is like the first step down that path. Take functions and let's represent them with just a line around some point. It's only a good approximation around some single point.
Yeah.
Okay, so when we use a linearization, we usually use big L for, here's our linearization. And it's just the tangent line. So let's calculate what the tangent line is to this function at this point.
Mm-hmm.
You with me?
Yep.
Well, first off, what's our basic equation for a line? Here's our point slope form.
Mm-hmm.
This is an equation of a line with that as a slope and goes through x1, y1. Right?
Okay.
Move the y1 to the other side. Here's our equation.
Yep.
So it's y equals something. Now, we're not calling this line y, we're calling it L of x.
Okay.
Good so far? What is the slope of this line? It's the derivative of that function f at that point. So what is the slope? It's the derivative of f at a. That gives me the slope of this function at the point a, which is the same thing as the slope of the tangent line at a.
Okay.
Okay? And then we have x minus, what's our x1? A. Plus, what's our y1? F of a. Because that line goes through the point a, comma, f of a. So we replace x1 with a, and y1 with f of a. And there you go, there's your linearization. That's all it is.
That's super simple. That's true for any function?
Yeah, for any function, at some point, here's its linearization.
That's super simple.
So here's the exact definition now. If f is differentiable at the point x equal to a, why do we need to be differentiable at that point?
Has to have it.
Because it has to have a slope, it has to have a derivative.
Oh, yeah.
So if f is differentiable at some point x equal to a, then this, Lx equal to f prime of a times x minus a plus f of a, is a linearization of f at a. And why do we do this? Well, notice that f of x is approximately the same thing as L of x, as long as we're close to a. As long as we stay close enough to that point a, L of x and f of x are pretty much the same thing.
That's not true for every function, is it?
Yeah.
It's going to be true for every differentiable function, if it's differentiable at that point. If it's differentiable at that point, I can always and forever zoom in enough on that function that you cannot see the difference between my line and your function.
You're right.
That will always be the case. All right, let's do a concrete example. Not a very useful example, just meant to give you intuition.
Okay.
Okay.
So here's our function, f of x. It's equal to 1 plus x. I graphed it here in green for you. We're going to find the linearization at the point x equal to 0, and at the point x equal to 3. Intuitively, what does the linearization give you? It gives you the tangent line at that point.
Mm-hmm.
So x equal to 0 should give us this tangent line. X equal to 3 should give us this tangent line. Don't read too much into my picture. So let's start at x equal to 0.
Okay.
Let's find that linearization. So that linearization, I'll call this L1. So we'll use L1 for this line, L2 for that.
0, isn't it?
L1 of x is equal to, first we need to find the derivative of the function at that point.
Yeah.
So let's put a pin in that for a second. Here's f of x. So what is f prime of x? Let me write f of x again in a more telling way just to help you guys. So that's 1 plus x to the 1/2, right?
Yep.
Okay, so now what is f prime of x?
1/2 1 plus x,
This is with respect to x.
and then negative 1/2,
Minus 1/2
times dx over dx.
and then
times dx if you want to think about it that way.
okay.
Sure.
Which is 1, right?
Which in this case, yeah, dx over dx is 1. The derivative of x with respect to x is 1. Okay, which is the same thing as, in case it's more useful to write it this way, 2 times the square root of 1 plus x. With me?
Yep.
Okay, so now we need to find f prime at the point we care about. Our linearization, our first linearization, what's the point we're doing it at?
0.
0. Our a is going to be 0. Sorry, am I covering it? A is going to be 0 here. So we're looking for what is f prime of 0 equal to?
0.
1/2.
Plug in 0 to this.
Oh.
It's 1/2.
1 plus 0 is 1. Square root of 1 is 1. 2 times 1 is 2. 1/2. See it? So, our first linearization is equal to, just blindly following the definition, it's f prime at the point we care about, times x minus the point we care about, plus f at the point we care about. Okay, that's just blindly plugging in without thinking. Now, what does this equal? F prime at 0 is equal to 1/2. Did I put an A there? Sorry. That's a 0. X minus 0 is x, so just times x. Plus, what is f at 0? What do we get when we plug 0 into our initial function? 1. So there's our linearization. It's a line with a slope of 1/2 and whose y-intercept is 1. Pretty close to what our picture's telling us.
Yeah.
Okay, now let's find our second linearization, L sub 2. Blindly, without even thinking about it, it's going to be f prime at 3 times x minus 3 plus f of 3, right? Just blindly plugging in, no thought.
Okay.
Okay, now what is f prime of 3?
4. Oh, right there.
It's gonna be
What's
1/4.
1/4, right?
Yeah.
1 plus 3 is 4, square root of 4 is 2, 2 times 2 is 4. Okay, so now this is going to be equal to 1/4 times x minus 3 plus, what's f of 3?
2.
2,
Oh,
right? Okay, so now this is equal to 1/4 x. Let's see, we have minus 3/4 plus 8/4.
oh yeah.
Minus 3/4 plus 8/4 is?
Sorry.
2 8s, 1/4.
Minus 3/4 plus 8/4.
Is 5/4.
5/4. Come on, guys.
Sorry.
5 times that is negative 3/4. 2 is the same thing as 8/4. Negative 3 plus 8, 5. Okay, there we go. So here is our second linearization. It goes, its y-intercept is 5/4. So on my picture, pretty good here, about 1/4 above 1. And the slope here, 5/4. Or not 5/4, 1/4.
1/4.
Yeah.
So there's our two linearizations.
Okay.
Make sense? Okay. Let's do another linearization. This time we're going to do the linearization of our cosine function at pi halves.
Okay.
So, our f of x here is equal to cosine of x. Right?
Yeah.
What is f prime of x going to be equal to? Because we're going to need our derivative.
Sine.
Negative
sign.
Negative sine of x.
Sine of x.
Perfect. So now, blindly, without even thinking, our linearization is going to be f prime at the point we care about times x minus the point we care about plus f at the point we care about. Blindly, without even thinking.
Yeah.
Okay. What is f prime of pi halves?
Negative sine x.
-1.
Negative 1. Plug in pi halves. What's sine of pi halves?
Sine.
Sine of pi halves is 1, make it negative.
Okay.
So that's going to be negative 1 times x minus pi halves plus, what is our function at pi halves?
Cosine.
0.
It's cosine of pi halves. What's cosine of pi halves?
0.
0, so plus 0. Or in other words, this thing is equal to negative x plus pi halves. So it's a line whose y-intercept should be pi halves and whose slope should be negative 1. My picture, way off. I wrote that way too steep.
Yeah. Gotcha.
Okay.
Okay. Let's do a more general one. This time, our function is 1 plus x to the k, and we're going to do it at x equal to 0.
Okay.
So, our linearization here, L of x is going to be equal to, first off, let's really quick think of what f prime of x is. If this is f of x, what's our derivative?
It's going to be k minus 1. Or sorry, it's going to be k times 1 plus x and k minus 1.
Perfect.
Times, well, yeah, I guess you.
Okay,
Okay.
so our linearization here is going to be f prime is 0 times x minus 0 plus f at 0, right?
Yep.
Blindly without even thinking.
Yep.
What is f prime of 0 going to be?
K
It's
squared
going
1 plus
to be,
x to the power k minus
0.
Plug in 0 here.
uh,
Or 1.
it's gonna be k minus 1.
What's 1 plus 0?
1.
1.
1. What's 1 to the anything?
It's
Take
the
1.
the
It's gonna be k.
exponent.
1 to any exponent is
1.
1. 1 times k is
Okay.
Okay.
k. So f prime here just comes out k.
Okay.
X minus 0 is
X.
X. Which is
plus f of 0. What do we get when we plug 0 into this?
You get
1.
1. So in general, the linearization for any function, regardless of what the k is up there, is k times x plus 1.
Okay.
We did a special case of that up here. This was 1 plus x to the 1/2. The answer was 1/2 x plus 1.
Okay.
But there's a common linearization that's fairly useful.
Yeah.
You're working with something like that close to 0, just treat it like that. Much easier to work with.
Is it useful in some cases to find the linearization of the general case of a specific function instead of trying to work with that specific case? Like if I have an example problem, are there cases where it's easier to solve the general case rather than the specific case you're working on?
I don't know what you mean by specific case. You mean once you have a specific A?
I mean, like for our first example, are there examples where it would be easier to solve a general case, like our third example, rather than solving a specific?
Well, sometimes you can come up with a general example that will give you some formula that you just know.
Yeah, that's what I mean.
It won't be easier to solve the general case than the specific case because the difference there is this one's going to have a concrete number where this is going to have a variable. So they're probably going to be identical. This one will just be a little bit harder because you have to keep track in your thinking. But we often look for general cases that we can solve that give us formulas that we can just remember so that we don't need to resolve every time we get something different there. Because now I can quickly ask you for what's the linearization of something like 1 plus x to the pi minus the square root of 2.
Pi minus the square root of 2 times
And
x
the,
plus 1.
right, and the linearization of that is just going to be pi minus the square root of 2 times x plus 1, and we didn't hardly even have to think about it.
Yeah.
The linearization of that around 0. That was for the special case where we care about close to 0, which is a common occurrence. That we care about a function's behavior close to 0. Okay, so we did a bunch of those examples. That's examples with linearization. There's linearization. There's the first half of the section. The second half of the section is differentials. What on earth is a differential? Here's the definition. It's going to be something it's easy to get tripped up with this. This is one of those things that a year after calculus might ask you about differentials. You're not going to remember how to tell me what they are.
Did you already tell us this?
I don't know. Okay, so let y be some function in terms of x. So let y equal f of x be a differentiable function. So it has a derivative everywhere on its domain. Good? Okay. The differential dy is this function. dy is equal to f prime of x times dx, where the differential dx is an independent variable.
Well, what do you mean by that?
In other words, dy here now is one symbol, dy, and it's a function that depends on two variables. It depends on what your x is, and depends on what your dx is. So dx here is going to be a variable, and dy is going to be an output. So dy is a function that depends on two variables, both x and dx. You need both those things to get a particular dy. Now we define our differentials, so that notice if I divide both sides of this equation by dx, then I get dy dx is equal to f prime of x. Now we already have notation dy dx, meaning the derivative of y with respect to x. This is not a quotient.
Yeah.
This is a quotient. So, it's very easy to get confused by these two things. dy dx, that we've been talking about up until now, anytime you saw this, this meant the derivative of y with respect to x.
Yeah. Right.
So why don't we write this so much different or something?
And, well, the reason that we don't is because now, look, f prime of x, there's a reason I wrote f prime of x here instead of dy dx.
Yeah.
But we could also write this as dy over dx is equal to the derivative of y with respect to x.
It's horrible.
And so, it is not proper to think about the derivative of y with respect to x as a quotient of differentials. But everybody does. And everyone pretends that those are identical, and they go on their merry way, because most of the time it just works out that nicely. Give you a quick example from the chain rule. When we did the chain rule, we said the derivative of y with respect to u times the derivative of u with respect to x. This is how we get dy dx, using the chain rule. dy dx, how do we do it? Assuming that y was equal to some function in terms of u, and u was equal to some function in terms of x. How do we get the derivative of y with respect to x? dy dx, it's dy du times du dx. If I were some physics professor, how would I prove that to you? I would say, well, just look at, cross out those two differentials, da da da, there you go. It's horrible, but it always works, almost.
Almost.
And so everyone always thinks about them this way. It's wrong, but it's how you're going to think about it.
Okay.
And when you go watch physics lectures, it's how they're going to talk about it. And they're going to just cross those things out left and right and have fun with it. Intuitively, we're always thinking about a dy. Our differentials, we're always thinking about them as a very small change in y. Our dx, we're always thinking about a very small change in x. And that's exactly what the derivative was. It's the limit of delta y over delta x as delta x approaches 0.
That's right.
So they capture very, very, very similar ideas. Don't let that confuse you for this section. That's why we separate these two. We don't say dy over dx was equal to f prime of x, even though you could divide by both sides.
Yeah.
When you see the dy by itself, it's very clear we're talking about differential. Right?
Right.
So that's
Can you give me some
derivative.
information on what a differential is?
We're going to do some examples to make this very concrete. So very concrete example. Here is some function, y equals x to the 5 plus 37x. We are going to find dy when x is equal to 1 and dx is equal to 0.2. You with me?
Okay.
So look at our definition of dy. dy is equal to f prime of x dx.
Point two.
Here's our f of x. So dy is equal to, what is the derivative of this?
5x to the power of 4 plus
5x to the
37.
power of 4 plus 37, right? So dy is equal to f prime of x times dx.
times
And dx is 1.
0.2.
Now, in our concrete case, x was going to be 1 and dx was going to be 0.2.
So dx is
So dy in that particular case is equal to, we plug in 1 for x, what do we get?
Same thing. Or 5 to the power of 4.
We're going to plug in 1 now. We're plugging in numbers.
42?
1 to the power of 4 is,
1.
we're going to plug in 1 now into our function.
Yeah. Okay, it's 1. Oh, 5 plus 37, which is 42.
42
Plus
times
0.2.
0.2, which is equal to,
Which is equal to
you can double 42 in your head.
Yeah, it's
84.
84, shift the decimal place, 8.4. Come on. Okay, so our dy in that particular case would be 8.4.
so what was dx? Like what was it actually? Like some variable?
It's just a variable. Intuitively, we are looking at how our function changes a little bit around some point when we change our x a little bit. So I'll give you the picture of it here in a second. It's giving us the same thing as a linearization.
Okay.
Well, not quite the same thing, but so there's a concrete example. There's how you use it. And it's just, you make the calculation and you plug the numbers in and a number comes out.
So why is it useful?
We'll use differentials a lot. They're very useful. And we will left and right go from something like, we would have said dy dx is equal to, if this were our function, we would have thought about that as 5x4 plus 37. And then we're just going to say, now treat those as differentials, and we get that dy is equal to 5x to the 4 plus 37 all times dx. And intuitively, we're going to think about dy as the derivative of y, and dx as the derivative of x. And we're going to be very naughty about it. Because that's what everyone does.
So we do what other people do.
Yes. But, for the time being, what is dy? It's a differential where it depends on these two variables.
Okay.
So dy is equal to f prime of x dx, where dx is another variable.
Just any random variable.
Any random variable, but notice that we define it so that dy over dx gives us a derivative. So we define our differentials so that their quotient always gives us the derivative. So that's why we often treat their quotient as a derivative, and the derivative as our quotient. And we go back and forth in our thinking like that. You'll see lots of examples with differentials, but for now, let's just get intuitively what this equation is telling us. Try and get some intuition for it now, right? Intuitively, if I were telling you I'm walking on a ramp, and the slope of my ramp is 1/2. Okay? The slope of my ramp is 1/2. I tell you I walk 4 meters down my ramp. How high did I go?
About 4 meters down you.
Yeah, so I walk 4 meters in the x direction. My ramp has a slope of 1/2. How high did I go?
2 feet.
2 meters.
Or 2 meters.
2 meters. So I give you my slope here. I told you how far in the x direction I moved, and that told you the change in my height. 2. If I tell you the slope, and I tell you how much I changed my x direction, that gives you the change in the height.
Oh, because it was.
Or in other words, slope is equal to delta y over delta x. That's exactly what this is telling you. It's telling you the small change in y when you have a small change in x and multiply it by the slope.
Oh, what the heck?
Exact same thinking, different symbols.
Okay.
So dy is just going to be the change in height. But it's not the change in height of your function. It's going to be the change in height of the linearization of your function. So it's close to the change in height of your function
It's not the same.
as long as you stay close to the point that you took your slope at.
So it's the slope of your linearization.
So f prime of x is the slope of your linearization, right? What do we mean by the derivative of a function at a point? We mean the slope of its tangent line.
Yeah.
Right.
So this is telling you the change in the height of the tangent line for a small change in x of the tangent line. And that's what it's giving you. So pictorially, let's show this, and let's do the quick algebra to try and smooth it all out. So setting up some other picture here has nothing to do with that example. Just some picture, here's some function f of x.
Okay.
Here's a, f of a. Here's a plus some distance. So dx here is just the distance between the 2 points.
Delta x.
Delta x dx, same thing, is going to be that distance. And here's the height at f of a plus delta x. Or dx, sorry.
Okay.
Good so far?
Yep.
We've got our linearization here, which is a tangent line, L of x.
Yep.
This distance right here is dx. This distance right here is the change in height of our linearization.
Which is dy.
We usually use delta y for that, but since our function is L, we're going to call it delta big L.
Okay.
Okay.
Right? I'm going to show that delta L is the same thing as dy. I'm going to show that delta L, the change in the height of our linearization, is dy.
Okay.
Right? So what is delta L? What is our change in height? It's our height at this point minus our height at that point.
Oh, yeah.
So what is delta L? It's the height at a plus dx minus the height at a.
Yeah.
Okay.
That's delta L. Good so far?
Okay.
Now blindly plugging into our function. Here's our function L of x. What do I get? Just to make sure we get this very clear. So really quick looking at this, what do I get if I plug 2 into that function? What is L of 2 equal to? If I plug 2 into this.
2.
No, it'll be,
It'll be f prime of a still. That no way depends on 2.
right.
Times 2 minus a plus f of a. If I plug in 2 to the function, it means replace all your x's with 2's.
Yeah.
There was only one x in there.
Yeah.
Okay, so what do I get now if I take L and I plug in a plus dx?
Well,
Was there an x in this part?
nope.
So that's still just f prime of a, that doesn't change. Times
A plus dx.
a plus dx. Keep going, what?
Which you just remove an a, and then
Minus a
plus f of a.
plus f of a. Good. And now, plug in, tell me what L of a is equal to.
L of a.
F prime of a times 0 plus f of a.
Where's your L of a?
Just plug in a for x.
Oh,
Replace all your x's with a's.
Okay.
There's only one x. What do I get if I replace that with an a?
0.
A minus a, which is 0, times that is 0, plus f of a. So when it's all said and done, we just get an f of a here.
Mhm.
You with me?
Yep.
So when we plug in L at a plus delta x, then we got f prime of a times a plus delta x minus a. Those will obviously cancel out. Plus our f of a. And then minus L of a was just another f of a.
Okay.
So you get f prime of a.
So those two f of a's go out, and that a go out, and you get f prime of a times dx.
Mhm.
F prime of a times dx is the exact definition of dy.
Okay.
So the change in height of our linearization is what we mean by dy here.
Okay.
Okay.
That's all it gives us, which is pretty intuitive. This is the slope of our linearization. Delta y tells us how much our linearization changes for some small value dx. I called that delta y, I meant dy. dy is equal to the small change in height of our tangent line for some small change dx.
Okay, that makes sense.
That's all it is, geometrically speaking. Good? Okay. Don't be scared of different notations that you'll see this with. So, here once again, I have f of x is equal to 3x squared minus 6. Let's find df.
Okay.
What is df? Tell me exactly what to write.
df is
We
going
can write
to
it
be
here.
f prime of x.
So what is that?
That's going to be 6x
Oh, okay. 6x,
minus 0.
which is 0. Anyway,
Uh,
and then
Yeah,
it's
times the
x
value,
minus a, which what does x turn to?
No, we're just using this.
divided by dx.
Oh, so I'm looking over
This was just giving us geometric intuition for what this meant.
So what's df?
I was proving to you that dy here is just the change in height of our linearization. So this whole thing was just to help you have a geometric understanding for what this is talking about.
Okay.
there. Okay.
We're talking about dy over dx is giving us the rise over the run of our tangent line. That's all it's giving us.
Okay.
Okay,
That helped. Is that it?
that's it.
Okay.
Look, always and forever you can check yourself, because what is df dx equal to?
6x.
What are you referring to? Oh, 6x.
6x. So df is better be 6x times dx, because that quotient better give you the derivative.
Oh, gotcha. Okay.
Okay,
That's
next, let's do a quick derivation for you. So I'm going to have two functions, u and v. So I've got some function u, I've got some function v. Question, what does du equal? If u somehow depends on x.
du
Equals
equals f prime of.
It equals the derivative of u, which I'm going to represent as u prime. You okay with this?
Yeah.
Okay.
Times
dx.
dx. Assuming it's some function in terms of x. Again, assume v is some function in terms of y. What does dv equal?
Why are you replacing some of them with u and not all of them? All the x's.
Because you still have dx.
Or your y and your x are both u.
Alright. U is some function in terms of x.
Mm-hmm.
v is some function in terms of x.
Why?
Why?
It should be v and y, shouldn't it?
Yeah. So here I have two functions in terms of x.
Okay.
Who cares?
Okay.
Now, what is du equal to?
Du is equal to
Derivative of u.
d prime of.
It's equal to u prime of x, but we don't bother writing that. We're okay with just writing u prime.
Okay.
When you understand that u is some function in terms of x times dx. And what does dv equal?
Oh, they're two different. Okay.
They're just two different functions.
Equals prime of v times dx.
Just want you to not get scared by different notation, all saying the same thing.
That makes sense.
Okay, now, what is the differential of u plus v equal to? It's going to be equal to
Differential.
u plus v prime, the derivative of those two things, whatever that is, times dx. Right?
Okay.
Okay.
Okay. What is the derivative of a sum? It's a sum of the derivatives. So this is equal to u prime times dx plus v prime times dx.
That's pretty straightforward.
And so the differential of a sum is the sum of the differentials. Sorry, this is equal to, that is the same thing as du, plus that is the same thing as dx.
PV.
Thank you. Good. Glad you're paying attention. So the differential of u plus v is the differential of u plus the differential of v. And ultimately, it just comes down to the fact that since the derivative of a sum is the sum of the derivatives, then the differential of a sum is going to be the sum of the differentials.
Does that apply for all of our?
That applies for all your rules. I'm not going to bother proving all these because it's the same thing.
Yeah.
So just to write it out, let you see in notation, what does that mean? That means the derivative of u times v, sorry, the differential of u times v is equal to the first times the differential of the second, plus the second times the differential of the first.
Yep.
And you do that with your quotient. What would be the differential of u over v? That would be the bottom times the differential of the top, minus the top times the differential of the bottom, all over the bottom squared.
Yeah.
Okay?
Oh, I see.
And u and v are just some functions.
Huh?
U and v are just some functions.
They're just two functions in terms of x and y, or in terms of x. They're two functions in terms of the same variable. Right? We don't know how to do our quotient rule. When I tell you, well, we can do it implicitly now, but when we were talking about our quotient rule, it was some function in terms of x over some function in terms of x again. We weren't looking at y squared plus 7 over z cubed minus 9 and applying the
Quotient rule.
quotient rule to that. It was, we had two functions in terms of the same variable. So it's understood, it's in terms of the same variable here.
That makes sense.
For our dx. But, I mean, they don't have to be in terms of the same variable, and you can still apply to this. It's just you're taking the derivative with respect to some variable. And so ultimately, y would have to be a function in terms of t, and z some function in terms of t if you're going to do that. If you take the derivative of it in terms of t. Otherwise, it's just 0, since it doesn't depend on acts like a constant. That's getting off track here. The point is, our differentials of these different things, they behave just like derivatives do. And so all our differential rules and all our derivative rules are the same.
That helps a lot.
Right. That's why everyone almost always thinks about differentials as the same thing as derivatives. And you're going to forget this definition.
So what is the same differentials? What do they do?
Well, one of the things that you see right out the door they do is they help us approximate these things. And notice that in the limit, it's going to get closer and closer to giving us precisely the derivative. That's the point.
So why
But-
not use the derivative?
Well, because oftentimes it's helpful to think about this as a quotient. And we're going to do problems where thinking about that as a quotient is very, very, very helpful. And so the differential is the definition that enables us to think about dy over dx as a quotient. Because the symbol dy dx is just a derivative of y with respect to x. That's not a quotient. The differentials are a quotient, dy over dx, where we defined them so that their quotient is exactly the derivative. So we will use differentials a lot. They're used a ton. And so very useful. But for now, we're just trying to get comfortable with it. Okay. Let's do a quick example. Find the differential of tangent of 2x.
So that's going to be the derivative.
So the differential of the tangent of 2x, what does this equal?
It's going to be the derivative of tangent of 2x times dx.
So tell me exactly what to write.
It's going to be secant squared of 2x.
Oh, you're just finding the derivative of that? Okay.
Basically, find the derivative, throw dx at the end.
Times dx.
And
Almost.
What?
then
That's
Times.
it 2.
2. So I guess we can put the 2 up front. And then we can put
Oh,
our
those
dx
are
here.
2 different terms.
Right?
Wait, where's 2 different? Sorry?
What's the derivative of 2x?
Just 2.
Oh.
It's 2,
Oh.
and then dx.
Okay. Sorry. Yeah.
Okay.
Okay,
Is that it?
that's it. It's just slightly different notation for something you've been doing over and over again. Very similar type thinking. These are very closely related to just calculating a derivative. dy is just the derivative of y with respect to x times dx. Then maybe write that out that way, and that will also probably help. What is dy? It is, by definition, dy dx times dx. That's what it is.
Oh.
So dy is the derivative of y with respect to x times dx.
See, okay.
And that's how people are going to think about it. And similarly, if I knew that y was some function in terms of u and u was some function in terms of x, I could have said dy is equal to dy du times du dx times dx. And notice that, obviously, says the physicist, so it's going to always, I don't know about always, but for pretty much every problem we come across, they're going to behave like that.
Why is
Sorry.
that true always?
I can't think of a good way. Notice our requirement here is that y was differentiable on its domain. So we may have to start being a little bit careful when maybe our function is differentiable at x, but since dx is moving a little bit, maybe somehow we can break that down. I don't know. So there could be places where it breaks. Don't ask me to think of them off the top of my head. I have no idea. Because almost always and forever, everyone thinks about it like that.
Strange.
Okay. I did that. Let's do this differential. What is the differential of x over x plus 1?
It's the derivative of x over x plus 1 times dx. So what's that?
D. That.
It's the derivative of
Is this the
x
quotient?
Low d high minus high d low, square the bottom.
Where are you getting 1?
Anyway, we go. What's the derivative of the bottom?
Oh, 1.
Well, plus 0.
Yeah.
Okay. And so on the top we get x plus 1 minus x. Or in other words, we get 1 over x plus 1 all squared.
I see.
Do we simplify that?
Oh,
Oh,
done
times
this
dx.
before.
Sorry. dx. dx.
And okay, that makes sense.
Not simplify?
Yeah. You don't want to unfactor it. Factoring is always nicer than... I shouldn't say always, but typically. Okay, we did those. Notice, here is f of a plus delta x. Here's f of a, right?
Yeah.
Yeah, okay.
Here is dy.
Okay.
Now notice that as our dx, if our dx were really small, obviously I drew my picture here so we could write symbols.
Yeah.
Notice that if dx were really small, then our dy is basically the same thing as this distance.
Huge, yeah.
Yeah.
So, notice that dy is approximately the change in height, f at some point minus f of a plus delta x minus f of a,
Okay.
that's this height,
Yeah.
is basically the same thing as dy for small values of dx.
dy. Doesn't that include
dy is this distance.
Yeah.
F of a plus delta x minus f of a is this distance.
Yeah.
Why are they equal to each other?
They're not. They're approximately the same. That means they're close.
They're
Oh, you're saying if it was.
If
Oh,
dx
okay.
is really small.
Yeah, okay, I got you.
Okay, it's just like what we were talking about with linearizations over here.
Yeah.
Is small defined precisely in any kind of way?
No, because it depends on how many decimal points you care about.
So let's just update interpretation.
Yeah, it's up to what you care about.
Okay.
So,
Arbitrary.
well, it's not arbitrarily
Ambiguous,
small.
that's-
You have to pick some distance, and it's going to give you some error.
Ambiguous.
And we'll do an example where we get some error. So we'll get to an example. Okay, we said that. Let me write this equation one more way. Another way we can do this is we can approximate some point f of a plus delta x by finding it. It's approximately the value at a plus r dy, moving this to the other side. You see that? So here's a common way that we use this equation. We don't want to work with our function directly. We're trying to approximate the function's value at some point. It's close to a point that behaves really nicely. And so we use this equation to approximate it at this point that's close to a nice point. Right?
Yeah.
We know what the sine function does at exactly pi halves. What does it do a little bit to the left of pi halves? How can we approximate that value?
Okay.
For example. I don't know if that will be a concrete example here, so now I'm just going to go through the examples the author has. Starting at example 6, page 170. Okay, so he says the radius r of a circle increases from 10 meters to 10.1 meters. Okay, so I've got some circle. And somehow I don't know, I can inflate it or something. I'm not sure how to make this physical. But my circle grows a little bit from being 10 meters in its radius to 10.1 meters.
Isn't that just convection?
Well,
Or conduction?
no. So,
Heating and cooling will do that.
oh, sure, you can think about it that way. I got some disk. It heated up so much that it expanded an entire 10 centimeters. A lot of heat somehow without melting. So our radius started out at 10 meters, and then our change in radius, our small change in radius, dr, is equal to 0.1 meters. That's how we're going to be setting up these problems and thinking about it. Okay? We are looking for an approximation in the change of area. So we are looking for dA. You with me?
Okay.
Now, what is our area formula?
Pi r squared.
Pi r squared. So what is dA?
dA equals
Oh,
pi r squared dr.
Just take the derivative.
it's 2 pi r.
Why?
2 pi r times dr. What is dA dr? What is the derivative of that with respect to r?
It's 2 pi r.
2 pi.
2 pi r. Throw the dr over there. Whoop.
Okay. Good.
There's a derivative of a with respect to r times dr.
So you're counting
Okay.
5.1.
And so now, what is our approximate change in our area then? That we care about. So the dA we care about. dA is equal to 20 pi times, what was that, 0.1?
Yeah.
So that's going to be equal to 2 pi.
Right.
That's approximately how much our area changed.
dr is more.
You have to-
Oh, okay. Okay, gotcha.
Wait, that's.
Wait, how can you?
Why is that
How
not
did
precisely?
you do that?
Why
How
is
did
that
you
not
get 2 pi?
precisely how much the area is?
Did I mess something up?
How did you get 2 pi?
Our r was 10
Yeah.
Okay, that
So
makes
20.
20 pi.
pi times dr was 0.1.
Oh,
What's
so
20
you
times-
shift it. Okay.
Sorry, let me write this as times, might help if I do 0.1 so you don't get confused with the dot. That better?
Well, I should just still know, but yeah.
Why is that just an approximation?
That's just an approximation. We used a linearization to get that. We didn't actually calculate the change in area. Let me actually calculate the change in area really quick. Because our linearization is going to be off a little bit. dy is not the same thing as the change in height of our function.
It never
How
will
would you
be.
graph the area of the circle, like you take?
It's just a function right here. It's just a parabola. So pretty straightforward, but let's calculate the actual change in area. So we're taking the area when our radius is 10.1. So that is going to be pi times 10.1 squared minus pi times 10 squared. And the answer comes out 6.3146 rather than 2 times pi, which is
6.14 or 6.28.
right. So this comes out to approximately 6.28319. The actual change is 6.3146. So I'll make that 2 since for some reason it's showing me a different number of decimal places on this.
So is there a way of finding your error?
Yes, there is a way to find your error. And your error is what the actual change was minus what you approximate the change to be.
Is there a way of doing it where it's not just an approximation, where you have like an algebraic?
Well, your linearization always gives you an approximation.
Right. I'm just wondering, is there a way to algebraically express your error so that it's a precise value or approximation?
Yeah, our error was equal to
Whatever that
f of our second point
subtract.
minus f of our first point. So there's the actual difference minus what we said it was going to be. And that's how much our approximation was off.
Which so little it doesn't.
So in this case, why are we even approximating it?
Well, in this case, this is a stupid easy equation. So we're intentionally being given an equation to see how close our approximation was to the actual answer. In practice, when you do this, is when you're working with equations that aren't easy. And so you linearize it.
And so approximation help.
So doing that for an area function is a stupid thing to do it for, because calculating the actual difference is so easy. The point is to give you intuition for what it's giving you in easy cases.
Okay.
Okay.
Yeah, so I guess symbolizing it, yeah, the author gives it, sorry, this was a dA in our specific example, right?
Yeah.
Yeah.
So the author, here's a nice little formula that the author gives you for the error. The error, in this case, is delta A minus dA. That's a good way to write it. The actual change in area minus the approximate change.
Which is intuition based.
Okay, let's try another one now. So our next problem, what we want to do is we want to approximate what 7.97, okay, so 7.97 to the 1/3 equals. Now what do we wish that number was? Imagine I gave this to you on an algebra test.
8.
You wish that that was 8 to the 1/3. So here's a point that you know how to work nicely with.
Yeah.
So this is going to be our A. Our A is a point that we know how to work nicely with. Here's a point that we're forced to work with. So this is our A plus dx. In other words, what is our dx in this case?
0.03.
Negative 0.03. Good?
Okay.
So now, our approximate value is equal to our actual value plus dy. So let's really quick get dy. We'll write that over here. So here's our function. Here's y. So what is dy equal to?
So that's our y.
It's going to be your derivative of 7.97 to the 1/3.
It's going to be, bring it down,
Holy crap.
1/3 x cubed. Our function, that's our function at a specific value. Here's our function in general. Y is equal to x to the 1/3. There's our general function.
Yeah.
Okay, so we're taking the derivative of this. Sorry, should have said that right. I wrote that 3. Okay, sorry.
2/3.
Times
Yes,
dx, right?
Yep.
Or in other words, it's just equal to, we can write this as 1 over 3 times x to the 2/3 all times dx. You with me?
Yeah.
Now we know our dx, and we know the point that we care about. We know our a that we care about.
Yeah.
So our dy in our concrete case, the x that we care about is
8.
the point that we're approximating around is 2. Or is 8. Yes, sorry. 2 is what we get when we plug it in. So this is going to be 1 over 3 times, what's 8 to the 2/3? You can square it to take the cubed root, or you can take the cubed root and square it. Doesn't matter which way you go.
4.
It's 4.
And then
You guys,
It's 4.
let me, 8 to the 2/3 is the same thing as, you can think about this as 8 to the 1/3
isn't it 6?
squared,
Okay.
or you can think about it as 8 squared to the 1/3, whichever way you want.
Which is 4 out of it.
What's the cubed root of 8? 2,
2.
because 2 times 2 times 2 is 8. 2 squared is
4.
4. That's one way to think about it. Or I could have said 8 squared is
60.
64.
64.
Or 64.
The cubed root of 64 is 4, because 4 times 4 times 4 is 64. In either case, this is going to be 3 times 4 times our dx, right?
12.
And so it's going to be, our dx is negative 0.03 over 12. So we're saying that 7.97 to the 1/3, the value we're approximating at,
Yeah.
it is approximately f at our nice point at 8. What's 8 to the 1/3?
2.
2 plus our dy, negative 0.3 over 12.
Okay.
Are you guys simplify that?
No, that's simplified enough. Let's just plug it in now and see what the numbers are. Are you doing the actual one or the approximation?
We both.
Okay. 2 plus negative 0.3 divided by 12 gives us, so our approximate value, we got 1.975. Notice that you could have done this by hand. You didn't need a calculator to do that.
Yeah.
Imagine you didn't have a calculator. How on earth would you have figured this thing out?
That's a good
You
question.
can do it like you should.
Now, plugging into our calculator, because we live in a day and age where we don't have to worry about how to figure that thing out,
It's pretty close.
then it comes out to 1.9975,
Roughly.
roughly. So, pretty close approximation.
We were off by.
So what's the point of showing us the approximations?
Yeah.
Are we?
That's what this dy gives you, is an approximation for the change in height.
Okay.
And as your delta x as your dx gets smaller and smaller and smaller, your dy becomes a more and more perfect approximation.
Yeah, that's.
And in the limit, it's obviously perfect because that's how it's defined.
Okay, that makes sense.
So let's finally do one that is a little bit more of a real problem. Let's try and estimate the height of a well. Here's how we're going to estimate the height of a well. We're going to take a rock and we're going to drop it and we're going to listen for the splash. Right?
Okay.
So
Pretty smart what I do.
we know from our physics class that an object falling, we can calculate its distance if we do it in feet.
9.81.
S is going to be 16 times t squared. We're doing it in
We should
feet.
do meters. But-
In meters, we'd have to do 9.8 over 2.
Yeah.
Okay.
So it's a bit uglier. Feet, it comes out nicer numbers. Okay, so there is our rock falling.
Mhm.
Okay, now let's say that we actually do this experiment. You got your stopwatch ready to go, and you try to click it and start it right when you drop the rock. You listen for the splash, and then you hear the splash and you try and stop it. We're going to assume that your error, your reflex time, is about 1/10 a second. Right? Because you aren't perfect. You can't start the stopwatch exactly when the rock falls and stop it exactly when you hear the splash.
Yeah.
So we're going to say to account for that, we're going to give a margin of 0.1 seconds. And we're going to say that on your stopwatch, it came out exactly 2 seconds when you heard the splash. Keeping our numbers nice and round.
Okay.
So we're trying to approximate the depth of this well.
Mm-hmm.
Good?
Yeah.
So we're calculating that the S here is equal to, what is S going to be when I plug it in here?
4.
4 times 16.
It's something.
64. 4 times 16, 64.
Oh, wow. It's so
64. But now, we got to do plus or minus our ds here.
Plus or minus. Where'd that come from?
Maybe you were too slow. You could have started a little bit late and made your time a little bit shorter, or made it a little bit longer. So what is our potential ds here now?
Why is it ds about dt?
Wouldn't it be minus?
Your position, our approximate position, is going to be what we actually get just from plugging in our number, plus our little error here. It's not technically the error.
It should be dt.
No, it should be ds. Look. Let me write it 2 ways. So we can have s, at t plus dt is equal to s at t. I should have written it like this to begin with. Or we could have had s at t minus dt is equal to s at t plus ds in that case where dt is negative.
Oh.
Because you don't perfectly time for 2 seconds.
Right.
Yes.
Right? You could have had there's a lag time on how long it takes you to actually click those things.
Right.
So you could have accidentally timed it for 0.1 seconds longer than you should have, or for minus 0.1 seconds longer than you should have.
Or anywhere in between.
Or anywhere in between. But these are our 2 extremes.
Right.
Okay.
Okay.
So this is going to be equal to, and notice that this is just going to be, so let me just, should have written it like this. Okay, I think that this, you'll all be okay with this now.
Why do you have 2 of them written? Oh, never mind.
Okay.
Well, it would still be plus ds, right?
Why?
Because if you do a minus here, then it's going to come out minus here. If you do a plus here, ds will come out plus. But if we're always just going to plus the dt here, we can account for the sign by doing plus or minus there.
How is that? If it's plus, it's plus.
Let's work out one concrete case before. Okay, well, we got these 2 cases. Let's just do it one at a time. All right, let's calculate this. So s of t plus dt, first thing we need to do is calculate ds. So what is ds going to be?
ds is
32t
yeah,
Keep going.
32t.
times
What did you take the derivative with respect to?
16 times t squared.
It'll be
ds
dt.
or dt.
dt. You took the derivative with respect to t. Look, you are saying ds dt is equal to 32t.
So you just.
Whoop!
Oh, look at that.
Would you look at that?
So simple.
You'll look at that a lot of times. There's our ds. It's just ds dt times dt.
Yeah.
Okay, there's our ds. Now, let's plug it in for each of these cases. So when dt is, when we added on the dt, then our ds here is going to be what?
3.2.
64 times 0.1.
64.
Whoa.
Oh, because you put a t.
Oh.
64 times 0.1, 6.4 feet. When the dt was positive. If the dt was negative, then it would have been equal to minus 6.4 feet.
That's a really short problem.
Whoa. Why are you timing? What?
Okay.
How does I see it, it just doesn't make sense. How does a 0.1 second mean so much feet? 0.1 of a second.
Yeah, you could be off by a decent amount. So the depth of our well, we're saying that the depth of our well, we are approximating the depth of the well, is approximately
Oh, I see it.
64 feet
Or
plus 6.4 if our dt was positive, and minus 6.4 if our dt was
That's like-
negative.
Or anywhere.
That's 12.8 feet range miss.
Yeah.
Right, so this is how off we could have been in our approximation. This is not a very accurate way to determine the depth of a well.
Is there a more accurate way to determine the depth of the well?
Well, yeah, stick a ruler down there.
Wow.
Stick a measuring tape down there. Or you could set up using lasers and some sort of sound system that hears a splash and make sure that you got to count that the sound wave goes has to come all the way back up the well, and you can get pretty complex keeping track of everything you want to count for. So yes, there's a lot of better ways to do this. You manually dropping a rock and using a stopwatch, not the best way, but it still gives you a pretty good feel for it.
12.8 LF.
It's not that
Potential, I guess.
Well, somewhere between 58 and 70 feet. Okay, that's not bad.
Yeah, you can do something like that.
Yeah. So there gives you a more useful example of how you might use something like that.
Huh.
Of course, we're going to see much better examples for how we use differentials. We'll use them a lot.
Okay,
I don't know if we will. They're used a lot in calculus, especially the more advanced you get. I'm not sure how much we personally will use them.
I like them. So.
Okay. Anyways, that's it for this lecture. That's it for the end of chapter 3. We did it. And we start chapter 4 next week. Any questions?